Imagine standing beneath a sky painted with shimmering colors, a place where the night comes alive with vibrant hues. Welcome to our journey into the heart of one of nature's most awe-inspiring phenomena, the Northern Lights. Known as Aurora Borealis in the Northern Hemisphere and Aurora Australis in the Southern Hemisphere, these lights are more than just a visual delight. They are a cosmic phenomenon that has fascinated humanity for centuries. From ancient myths to modern science, the Northern Lights have always been a source of wonder and intrigue. In this video, we will unravel the mysteries behind these luminous displays, exploring their origins, their breathtaking beauty, and their significance in our world. So, prepare to be amazed as we dive into the science, the stories, and the sheer magic of the Northern Lights. Let's embark on this celestial journey together. And now, let's delve deeper into the enigmatic Northern Lights. To understand the Northern Lights, we must first journey to the heart of our solar system, the Sun. Our Sun, a colossal ball of burning plasma, constantly emits a stream of charged particles known as the solar wind. This solar wind travels through space, carrying with it the raw energy needed to create the auroras. When these charged particles reach Earth, they encounter our planet's magnetic field, a protective shield that deflects most of the solar wind. However, some particles become trapped within the magnetic field and are funneled towards the polar regions. Here, the charged particles collide with gases in Earth's atmosphere, such as oxygen and nitrogen, resulting in the dazzling light displays we know as the Northern and Southern Lights. The type of gas and the altitude at which these collisions occur determine the colors of the auroras. For example, oxygen at higher altitudes produces red auroras, while at lower altitudes it produces green. Nitrogen, on the other hand, can create blue or purple hues. This dance of particles and light is a direct result of the interplay between solar winds and Earth's magnetic fields, creating a natural light show that is both scientifically fascinating and visually stunning. Now that we have a grasp on the cosmic forces at play, let's dive deeper into the enigmatic Northern Lights. While the interplay between solar winds and Earth's magnetic fields creates the foundation for the Northern Lights, the intensity and frequency of these displays are significantly influenced by solar activity and geomagnetic storms. Solar activity, such as solar flares and coronal mass ejections, CMEs, can dramatically impact the strength and visibility of the auroras. These explosive events on the sun's surface release vast amounts of energy and charged particles into space, which can reach Earth within a few days. When these particles collide with Earth's magnetosphere, they can trigger geomagnetic storms, causing the auroras to become more vivid and widespread. Geomagnetic storms are classified by their intensity, ranging from minor to severe, and are measured using the KP index. During a strong geomagnetic storm, the auroras can extend to lower latitudes, making them visible in regions that rarely experience this phenomenon. These storms not only enhance the visual spectacle, but also have practical implications, potentially disrupting satellite communications, GPS systems, and even power grids. Understanding the connection between solar activity and geomagnetic storms is crucial for both appreciating the awe-inspiring beauty of the Northern Lights and preparing for their potential impacts on our technological infrastructure. With this knowledge, let's continue our journey into the mesmerizing world of the Northern Lights. As we delve deeper into the mysteries of the Northern Lights, understanding the science behind their vibrant colors is essential. The dazzling hues of the auroras are a result of complex interactions between solar particles and the gases in Earth's atmosphere. When charged particles from the sun collide with oxygen and nitrogen atoms high in the Earth's atmosphere, they excite these atoms, causing them to emit light. The specific colors we see are determined by the type of gas and the altitude at which these collisions occur. Oxygen at higher altitudes produces the most common green and yellow hues, while at lower altitudes it can create rare red auroras. Nitrogen, on the other hand, contributes to the blues and purples that sometimes streak through the sky. The intensity and variation of these colors depend on several factors, including the energy of the incoming solar particles and the density of the atmospheric gases. This intricate dance of particles and light creates the mesmerizing display that enchants observers around the world. As we continue our journey, let's appreciate not only the beauty, but also the fascinating science that illuminates our night skies with such awe-inspiring splendor. Beyond their scientific marvel, The Northern Lights hold profound cultural significance for many indigenous peoples and communities living in the polar regions. For centuries, these ethereal lights have been woven into the fabric of myths, legends, and spiritual beliefs. The Sami people of Scandinavia, for instance, regard the auroras as the energy of their ancestors, dancing in the sky. In Inuit folklore, the lights are believed to be the spirits of animals, guiding hunters through the dark winter nights. These stories and beliefs highlight the deep connection between humans and the natural world, a bond that transcends time and geography. The Northern Lights serve as a reminder of the beauty and mystery of our planet, inspiring awe and reverence in those fortunate enough to witness them. To many, the auroras are not just a visual spectacle, but a source of inspiration and reflection, sparking creativity and a sense of wonder. They remind us of our place in the universe and the interconnectedness of all things. As we marvel at the Northern Lights, we are reminded of the stories that have been passed down through generations, enriching our understanding and appreciation of this magnificent phenomenon. Now, let's continue our journey and delve deeper into the enigmatic beauty of the Northern Lights. Welcome to our exploration of the Northern Lights, or Aurora Borealis, a stunning spectacle that is truly a cosmic ballet danced in the night sky. These lights are visual poetry, a celestial phenomenon that paints the polar skies with breathtaking colors. For ages, they have captured the imaginations of cultures around the world, inspiring folklore, art, and scientific inquiry. The aurora is nature's own luminescent show, featuring vibrant hues of green, purple, blue, and sometimes even fiery reds and oranges. This phenomenon occurs predominantly in high-latitude regions around the Arctic and Antarctic. It is no surprise that many travelers venture into cold, often remote areas, braving the chill to witness this mesmerizing natural display. The lights appear to dance across the sky, shifting and pulsating with an ethereal glow that enchants viewers. The experience of watching the Northern Lights is often described as magical, a once-in-a-lifetime encounter with one of Earth's great mysteries. Understanding the Northern Lights involves peering into the complex interactions between the sun's energy and Earth's magnetic shield. It's a story of particles and power, of invisible forces that illuminate our upper atmosphere. This essay will delve into the scientific mechanisms behind the aurora, explore factors that affect its intensity and appearance, and describe the stunning visual experiences they create. The aim is to unravel some of the mysteries behind why the Northern Lights shine so brightly. The Northern Lights begin their journey about 93 million miles away on the surface of the Sun. Our star continuously emits a stream of charged particles known as the solar wind. This wind travels through space, carrying with it pieces of the Sun's own magnetic field. When these charged particles reach Earth, they meet the magnetic shield that surrounds our planet, known as the magnetosphere. This initial interaction is crucial for the development of the aurora. As these solar particles collide with the Earth's magnetosphere, they are funneled towards the poles by the magnetic field lines. This is due to the magnetosphere's tendency to weaken at the poles, allowing solar particles to enter Earth's upper atmosphere. Once in the atmosphere, these charged particles begin colliding with gas molecules, such as oxygen and nitrogen. These collisions are the heart of the auroral light show. They excite the atmospheric gases, causing them to light up and create the beautiful colors typical of the Northern Lights. The colors of the aurora are determined by the type of gas molecules involved and the altitude at which the collisions occur. Oxygen, when excited at altitudes of around 60 to 150 miles, emits a brilliant green, the most common color of the aurora. At higher altitudes, it can also produce a rare, alluring red. Nitrogen, on the other hand, tends to generate blue or purplish-red hues. This fascinating interplay of elements crafts the stunning visual palette that lights up the polar skies. These processes are continuous and dynamic, influenced by the ever-changing conditions both from the sun and within Earth's magnetic environment. The science behind the aurora is not only about the beauty it creates, but also about the dynamic and powerful interactions that occur in the near-Earth space environment. This understanding helps scientists predict when and where the aurora might be most visible, aiding aurora chasers and researchers alike. The intensity and frequency of the Northern Lights are not constant. They fluctuate in accordance with the sun's activity. The sun goes through cycles approximately every 11 years, moving from solar minimum, with fewer sunspots and less solar activity, to solar maximum, with more sunspots and increased solar activity. During solar maximum, the sun emits more solar flares and coronal mass ejections, CMEs, intense bursts of energy and particles, which can have profound effects on the intensity of the aurora. When these solar flares and CMEs reach Earth, they can cause geomagnetic storms, temporary disturbances in Earth's magnetosphere. These storms enhance the flow of charged particles into Earth's atmosphere, often leading to more spectacular and widespread aurora displays. Geomagnetic storms are rated on a scale from G1 minor to G5 extreme. The stronger the storm, the further south the northern lights can often be seen, sometimes reaching latitudes atypical for auroral activity. Apart from solar activity, the orientation of the interplanetary magnetic field, IMF, which is carried with the solar wind, also plays a crucial role. When the southward component of the IMF aligns opposite to Earth's northward magnetic field, it opens a gate for solar winds to enter the magnetosphere more efficiently. This process, called magnetic reconnection, enhances the intensity of the aurora by increasing the energy transferred into Earth's magnetic field. Understanding these factors is not only crucial for predicting when the aurora will occur, but also for preparing for potential disruptions. Strong geomagnetic storms can interfere with satellite communications, GPS systems, and even power grids. Therefore, monitoring solar and geomagnetic activity is important not only for aurora enthusiasts, but also for maintaining the integrity of modern technological systems. Section 4. A tapestry in the sky, describing the visual splendor. The visual experience of the northern lights is nothing short of theatrical. Imagine standing under a vast, starlit sky, suddenly awash with waves of color. It starts with a faint glow on the horizon, then gradually the colors spread across the sky, forming swirling patterns of light. These lights can form curtains that wave, arcs that stretch across the sky, or spirals that twirl dynamically. Each display is unique, a fleeting masterpiece crafted by nature's invisible hand. The colors themselves tell a story of altitude and atmosphere. The most common hue, a brilliant green, is produced by oxygen molecules located about 60 miles above the Earth. Sometimes, particularly during strong solar events, the sky is graced with deep reds, a rarer sight, caused by high-altitude oxygen at about 200 miles up. Mixed in might be hints of purple and blue, courtesy of nitrogen. The result is a luminous dance across the celestial dome, a spectacle of light and motion that captivates and mesmerizes. These natural light displays are not just beautiful, they are also instructive. They remind us of the dynamic nature of our planet's relationship with the sun and the forces at work in the space surrounding us. For photographers and nature lovers, the aurora offers a challenging yet rewarding subject, a chance to capture a moment of transient beauty. For scientists, each appearance provides valuable data about the interactions between solar winds and Earth's magnetic fields. Section 5. Conclusion.